So what have I made you watch so far? Measuring area incrementally and calling that dA. In rectangular coordinates, it's dy dx, dx dy. Polar coordinates, it's r dr d theta. Made you look at changing volume incrementally. And depending upon your coordinate system, that incremental change in volume, that measure of volume, dV, maybe dy, dx, dz, rearranged. R, dz, dr, d theta, if you're using cylindrical coordinates. Rho squared sine of phi d rho dv d theta, if you're using spherical coordinates. Then I had you look at incremental changes in length and using that as a measure over which we can integrate. And that was just like arc length. It was just like arc length. Actually, it was just an extension of Calc 1 integrals. Wasn't that bad? Now, changes in surface, using surface as our measure, using surface as our basis for determining stuff. Some surfaces are hard, but like this coffee mug, if I put hot water into it, I will start to feel the heat emanate from the surface of my cup. And where the heat emanates and how hot it is in various places is going to be a function of all kinds of stuff, including how hot the water is in different spaces, how big the opening is at the top, all kinds of stuff. Stuff flows in, stuff flows out. Surfaces are important. Well, up here, I have a very busy board again for you. Here is a swath, a swatch, a chunk, a snipped out piece of a three-dimensional surface. My three-dimensional surface is given to me as z equals LF of xy. And as before, which suddenly I feel like I was missing a z. I don't remember if I was. Big F of xyz is going to be little f of xy minus z. That's technically equal to 0 because of what's written above. I don't really need it, but I wrote it up there anyway. If I slice my space up into tiny enough little chunks, slice my surface up into tiny enough little swatches, those tiny little swatches are going to start to look like planes. Well, more like rectangles in 3 dimensions. And if I consider the sides of those to be like, I don't know, vectors, and I identify one corner of this swatch, almost rectangular chunk of my surface, I call one of those points P and say it's got coordinates XY. I should probably subscript it with zeros to say it's a specific spot. Not worried about that right now. This vector A, which starts at P and goes forward only in the X direction, because I can go in any direction I want, and I'm choosing to go towards you. It has an incremental change in X, no change in Y, but the change in three-dimensional height from the point P to wherever I stopped after my incremental step of X is going to be, it's a differential. It's the partial with respect to x, delta x. Now, why the delta x on the end? Keep in mind that I am in 3D. That is part of my total derivative. It's the part of the change in z that depends only upon x. So think about your total derivative. That's the part of z that changes only with respect to x. So it's half of my total derivative of z. For this vector that I've called b, which is either running along the back or the front, however you want it to be, I've decided to make that point in the direction of positive y, so that I'm not changing x at all. Get that 0 coordinate, makes me happy. Y will change by a little bit. And what will z change by? Well, the part of the total derivative that is impacted only by y. Now, the total derivative has as its second term, partial with respect to y, dy. I have an incremental change, so I change that dy back to delta y. There's my incremental change in delta z with respect to y only. Now, I have a rectangle in space, and I have a vector on one side and a vector on the other side, and it doesn't even have to be a rectangle anymore. It can be a parallelogram now. I made it a rectangle, but it doesn't have to be. To find the area of a parallelogram formed by two vectors with the same initial point is the magnitude of their cross product. Now, if you'll trust me, there is the x component or the first component of the cross product squared. There's the second component or the y component of the cross product squared. And there is the z component of the cross product squared inside the square root because I'm taking the magnitude of the cross product. If you don't believe that that's what goes inside the magnitude, go ahead and do the cross product of these two vectors that I've called A and B. Now watch it here. There is a square on everybody. There's plus signs in between things so I don't get to make stuff go away. But everybody's got a delta x, delta y. So if I factor out a delta x and a delta y squared out of the square root, I can't I? Yeah, I can. So if I factor that out, all I'm left with is the partial with respect to x squared. Forgive me for shorthanding, but I've got less space. Partial with respect to y squared, and again, forgive me for shorthanding, plus, well, factor delta x, delta y off of delta x, delta y, and I have 1 left. So I called this delta t because it's kind of like a tangent plane. It's an estimate for the area of the swatch I cut out. And so delta S can be approximated by that square root. Now there is another way for me to write that, and I've done so here. Square root of the partial with respect to x squared of the little f, function that defines my surface, partial with respect to y squared, plus 1 dA. Notice I replaced that with dA. I didn't say dy dx or dx dy. I said dA because it's an area measure, okay? Because sometimes I'm going to want to pull out polar coordinates and not x's and y's. So it's good to go ahead and learn that measurement, that ds measure, as a dA measure. So then if you need to use r's and thetas, you can use r's and thetas. There's one more thing I want to point out to you about this. Now, I said I really didn't need this written up here, but I wanted to write it, well, because Yeah, I want to write it. Is this the same as saying the magnitude of the gradient of big F with a dA on the end? Is it the same as my surface measure? Big F. It's partial with respect to x is whatever F's partial with respect to x is. It's partial with respect to y is whatever F's partial with little f's partial with respect to y is. And it's partial with respect to z is minus 1. So remember, gradient of big F is little f sub x, comma, little f sub y, comma, negative 1. And then the magnitude of the gradient, magnitude of a vector, you square components, add them up, throw a square root around them. That's exactly what's inside here. There's the me that loves this version of the formula at certain times. And then there's the me that loves that version of the formula at certain times. They're identical formulas. They're the same. It's back to the whole big F, little f. Ooh, which one means what? I made you watch. Probably made you watch more videos than you want to watch. And you're feeling maybe a little terrified because I haven't really given you much yet with all these new ideas of measuring things. Trust me, please trust me. I'm going to get you used to the notation. I'm going to get you used to the concept of referring to these as measures. dx back on an integral is a measure. Horizontal measure. dy back in Calc 1 is a measure. dA, area measure. dV, volume measure. d little s, length measure. d big S, surface area measure. Surface area measure. Integrals after Thanksgiving. Integrals after all of this. And after you're comfortable writing these and rewriting these and looking at them and telling me stuff. See how it goes. It truly is all downhill from here. Not downhill in a bad way. We are so close to being finished. For those of you who desire context, I promise you, context is on its way. But sometimes we need tools before context. Remember, you had to learn the quadratic formula before anybody ever really let you graph a parabola. So this is kind of like me making you learn the quadratic formula and you go, why? Actually, let me change that. Remember how you had to learn to complete a square? Nobody really told you why. And then you had to learn the quadratic formula. And you may remember or may not that that's just a generic result of completing the square process. And then suddenly, like years later, somebody says, oh, and now we're going to graph this parabola and we're going to find its x-intercepts. And you may or may not have made the connection that this is why they made me learn the quadratic formula a long time ago, so that I could quickly find the x-intercepts of a parabola without having to go back and complete the square. So I'm at the completing the square stage where you're wondering where we're going. We're going to the